All right, have you ever heard of a physics hack? Well, today we're going to dive into one that is it's brilliant. And it's surprisingly simple, but it could give solar panels a massive power boost.
So let's just start with a quick question for you. When you picture a solar panel, just soaking up the sun, what do you think is its single biggest enemy? Believe it or not, it's a total paradox. The very same thing that gives the panel its power is also its biggest threat: heat. All that solar energy creates a ton of heat, and that heat literally it slowly cooks the panel. It drains its efficiency, and yeah, it can even shorten its lifespan.
Okay, so here's what we're going to cover. We'll start with solar power's heat problem, look at a cool idea with floating panels, break down a self-powered cooling system, and then see how a simple test led to finding the economic sweet spot.
So, first things first, just how big is this heat problem? Well, it's huge. Get this. For a typical solar panel, a staggering 80%, 80, of the sun's energy is just wasted as heat. It's not converted into electricity. That is a ton of lost power.
Okay, so what was the first big idea engineers had to tackle this? Well, they literally moved entire solar farms from land onto water. And this created what we now call floating photovoltaic systems, or FPVs for short.
And these FPVs have some really great side benefits. They save on land use, they can reduce water evaporation from reservoirs, they even help suppress algae growth. But for our story today, the most important thing is that the water itself acts like this giant natural heat sink, constantly pulling all that damaging heat away from the panels.
But this got researchers thinking, okay, this natural cooling effect, it's good, but could it be even better? What if we could somehow supercharge this whole cooling process, but, and this is the key part, without using any extra energy? No pumps, no fans, literally zero extra power. Just physics.
And that question brings us to the absolute star of our show today, something called the Natural Convection Cooling Loop, or NCCL for short. This little device is right at the heart of all this research.
So what is it? Well, imagine a cooling system that's completely passive. We're talking no moving parts, no external power source needed at all. It's basically a self-running engine that's powered by one of the most basic laws of physics you can think of. Hot stuff rises. And that simple principle, what scientists call buoyancy-driven flow, is what creates this amazing continuous cooling cycle.
Okay, so this diagram really shows you how simple the setup is. You've got these heat-absorbing pipes right on the underside of the solar panel. They run up to a little coolant reservoir at the top, and from there, another set of pipes goes right down into the cool water below. That's where it's going to release all the heat.
So here's how that cycle actually works. It's pretty elegant. The panel heats up the fluid in those pipes right underneath it. Now, because that heated fluid is less dense, it naturally starts to rise. Simple, right? As it rises, it pushes the cooler, denser fluid from the reservoir down. That cool fluid then flows through the pipes that are submerged in the water, releases all its heat, gets chilled, and then gets drawn right back up to the panel to start the whole thing over again. It's just this continuous, beautiful, self-powered loop.
Okay, now here's where it gets really interesting. This kind of system, this NCCL, it wasn't a brand new idea, but the researchers noticed one incredibly simple design detail that apparently everyone else had just completely overlooked. They decided to focus on just one single thing: the height of that top reservoir. Could simply moving that thing up or down really change how well the whole system works? It seems like such a tiny detail, right? But what if? What if it had a huge impact? So, to find out, the team basically put their hypothesis on trial. They ran a bunch of detailed computer simulations first, and then they went and built actual, real-world experimental models just to see what would happen when they tweaked that one single variable. And wow, the results were crystal clear. Just look at this chart. The higher they raised the reservoir, the cooler the panel got. We're talking raising it from 250 millimeters all the way up to 1250 millimeters, dropped the panel's average temperature by more than 3 degrees Kelvin. That is a really significant improvement. So why does a cooler panel even matter? Well, it's simple. For every single degree you can cool a solar panel, you get a boost in its efficiency. And this chart, this shows a dramatic effect. Check it out. At the 750 millimeter height, the efficiency jumped by a massive 17.84%. That's not a small number.
Yeah, let's just pause on that number for a second. Almost an 18% increase in power output. And this wasn't achieved with some crazy new exotic material or a super complex technology, no. It was done just by optimizing the height of a pipe in a passive cooling system. That is a huge win for such a simple design change.
Okay, so right now you're probably thinking, well, duh, just build the reservoir as high as you possibly can. But, in the real world, great engineering isn't just about maxing out performance. It's always about balancing that performance with cost.
So, now let's talk money. Let's look at the economics. The researchers calculated something called the levelized cost of electricity, or LCOE, and the payback period for each design. And what they found is fascinating. The 750mm design, it actually had the lowest cost and the fastest payback period. We're talking just over 7 years.
So get this, even though the 1250mm reservoir was technically a little tiny bit more efficient, the extra cost to build it that high, it just wasn't worth the tiny additional power you'd get. The 750mm height was the economic sweet spot. It's that perfect balance of cost and performance.
And the researchers, they summed it up perfectly in their paper. Basically, once you go beyond 750 millimeters, you hit a point of diminishing returns. That teeny tiny extra boost in efficiency, it just wasn't worth paying for.
This whole thing is just such a powerful reminder that sometimes the biggest breakthroughs aren't about inventing some crazy new material. Sometimes it's just about cleverly applying simple design principles to old problems. And it really makes you wonder, doesn't it? What other simple physics hacks like this are just out there waiting to be discovered, ready to help unlock our clean energy future?